Good afternoon. My name is Balint Vasiljevic, and today we will hold a webinar about the new seismic analysis features of the latest ConSteel 11 software version. Sorry. For those who are not familiar with this webinar system, you may see on your screen such a floating panel which you can hide by pressing on the red arrow. If you might have some questions, then you can see also an edit table where you can type your questions. Your voice cannot be heard, so your only chance to ask a question is to type into this box. Depending on how quickly we will finish this webinar, which is planned to last till 2 o'clock, I may try to answer the questions which appear here, or if there is no time left or the question is more complicated, then of course we will answer those questions later by email or by any sort of communication as usual. So let's start. ConSteel 11 included several new functionalities. Many of these new functionalities were arranged around seismic design. The seismic design is quite a complex design procedure, which may require also dynamic analysis to be executed, plus additionally the full procedure of designing a structure, including strength and stability calculations, is the task of the engineer. In order to be able to follow successfully this webinar, it has been assumed that the audience of this webinar has a basic knowledge about the theoretical background of seismic analysis, especially Eurocode 8. Additionally, it has also been assumed that the user knows the functionality of seismic design as implemented today in the previous version of ConSteel 10, because I will speak about the differences and see what are the additional features compared to the previous version 10 implementation. And then I will also assume that the listener knows how to perform stability verifications using ConSteel. Of course, if somebody doesn't have this experience, it doesn't mean that we may not be able to follow the webinar, but will be easier to understand the explanations. This webinar will focus on 5 different aspects. I will show some words about the previous version, what was implemented, just to be able to see the differences. I will speak about the different steps and different new possibilities regarding how the analysis can be done. And then at the end, I will show also 3 examples, from a simple one to a bit more complicated one, which will hopefully help to understand what are the differences between the several methods and what are the benefits of those methods. Seismic analysis in ConSteel 10. The main focus was on an easy use of this feature, especially also for engineers from those countries which are not specifically seismic affected. So it includes most part of Europe, where if somebody makes a design calculation for a steel structure, usually the building is located in a region where the seismic activity is not extremely high. Therefore, very often for steel structures, the low dissipative design category is used. In such a case, the design calculation can be quite well automated, and the ConSteel 10 has tried to support as much as possible this activity. As a side effect, several parts of this functionality worked as a black box, not letting the user to see some intermediate results, which is an understandable critics if somebody needs to design a building in a region of Europe or any other location where the seismic action is of higher importance and prefers to make a design based on DCM or DCH categories where there are several special requirements for member design and connection design. And for such purpose, the results as presented by ConSteel 10 might not be sufficient. As a side effect of the implementation of Eurocode 8 requirements, which was based solely on the CQC combination mentioned by Eurocode and by several modern standards, it has created such a set of results which were unfortunately not compatible with the stability procedures, stability calculation methods implemented into ConSteel. That's why, as a side effect for those combinations, for those ULS combinations which included seismic effect, stability verification was not possible using ConSteel 10. And then there were some smaller verifications like interstory drift and second order sensitivity, which are required by Eurocode, but these were not implemented in ConSteel 10. Again, usually these are less important for a building which is designed according to the DCL concept. Some words about stability calculation in connection of seismic design. In ConSteel, basically there are three ways to show the adequateness of a structure against loss of stability. These are pretty different methods. At least the first is very different from the second and the third. The first version, which can be reached in ConSteel under the menu member check, is basically a somewhat supported method of the procedure as described in Eurocode standard, based on calculated internal forces and buckling lengths, which must be defined by the engineer. Here ConSteel can help because by studying and analyzing the internal force diagrams can propose directly critical moments and critical normal forces, but finally it remains the responsibility of the engineer to define the buckling lengths. And once the internal forces and the buckling length, once the cross sections and buckling lengths are known, based on different interaction formulas, the resistances can be calculated and compared with the internal forces. So this is the well-known method of Eurocode 3 for stability verification. It must be also noted that this method is quite limited, mainly for double symmetric, uniform eye sections and similar sections. So if somebody, for example, wants to design a structure which might have asymmetric sections or even non-linear, non-uniform along its length, then these interaction formulas are not fully applicable. And then there are two different additional methods, which is the preference in ConSteel, and we call it as high-level advanced possibilities. The result of these can be reached under the global check menu, and there are two options of it. One of it is based on the slenderness values calculated based on buckling shapes, buckling modes, calculated using a linear buckling analysis. And then once we know the critical multipliers for each interesting section, and of course we know the internal forces, we can calculate a slenderness value, and then the rest is already as defined in Eurocode general method. There is also a subversion of this approach, pretty similar, where instead of directly calculating slendernesses, we apply the imperfection, the buckling modes as imperfection on the structure, and by performing a second order analysis, a simple cross-section verification is enough to prove the adequateness of the structure against loss of stability. As I said, these second and third are those methods which are favorized by ConSteel. Unfortunately, as one might see, these are strongly related on linear buckling analysis and second order analysis. In order to be able to perform linear buckling analysis, we need loads. all the traditional loads like wind load, snow load, live loads, every other type of loads are loads which can be organized into the right combination, and for this load combination one can calculate any number of different buckling shapes. Unfortunately, the preference of Eurocode by requiring to combine the multimodal results using a non-linear quadratic method, which is this CQC method, the result of this approach is not a consistent set of force which can be used as a force and calculate internal forces and buckling shapes as usual, but this is a set of maximum values in each sections of the structure regarding the type of internal force and displacement which is analyzed. So the result is a diagram of actions and displacements which can be added to the effect of the other loads which must be considered in a seismic combination, but unfortunately this approach doesn't let ConSteel to perform the stability calculations as planned and as ConSteel is set up. So this is the reason why in ConSteel 10 stability verification was not possible for those ULS combinations which included seismic effect. In ConSteel 11 we improved the situation and we included several additional calculation methods which are resulting forces, and these forces are then without any problem already applicable with the well-known procedure of Eurocode for stability verifications. This is just a well-known diagram, for example, of bending moment diagrams. As you can see, everybody who is familiar with seismic design has already seen such diagrams. These are typically diagrams where it definitely makes no sense to study the shape of the diagram to try to come up with M-critical or N-critical values, because it's not meant to be used like that. In order to have the software working less as a black box and more as a useful tool for the engineer, we made it also very transparent, the definition of the masses which will be considered during dynamic analysis. As you may know, in ConSteel 10 there was an option to select which are those load cases which will be converted into a mass, but nothing more was visible. There was no any feedback if this conversion was done or not done, and there was no really visible control. Very often it happened that somebody by mistake has forgotten to include a load case as a converted mass, and of course in such a case the result was not correct. We included the concept of masses. So in the software now we clearly separate forces, loads. These go into load cases and load combinations, and we have masses. Masses go similarly into mass cases and mass combinations. Additionally to the seismic analysis, which is based on masses and dynamic analysis, we made it also possible that the user can clearly manually define loads, which is called by the user as a seismic load. Such loads may come from any sort of external study or hand calculation as such. If a load case is called as seismic load case and these manually calculated forces are introduced, then later on for ConSteel this is equivalent to a set of results, force results, which are calculated with the dynamic calculations. It means that all the other seismic combination related verification can also be performed. So somebody might have a building which is designed in a region where not Eurocode 8 is the code to be followed but something else, then can still manually calculate the forces and apply on the structure. And one of the most important thing for visualization of the sub-results is that now the user can see all the forces generated by the software based on the mass participation of each vibration mode. At each node the user can see the force which has been calculated, and for each vibration mode we can see separately bending moment, all the internal force diagrams and displacement, reaction force, everything. So we give a full control to the user to understand how the structure works and responds on a seismic excitation. As I said, one of the main one of our main interests was to provide way to perform the high-level efficient stability calculations for those combinations which include the seismic effect. So we included several calculation methods which I will present in detail. The software is mainly based on Eurocode 8. As you may know, each member state which has introduced Eurocode has the option to prepare a so-called national annex, which might contain several NDP parameters. Many of these NDP parameters are included in the software. Additionally, some countries decided not to introduce directly Eurocode but make a national standard which is quite similar to Eurocode, but it's still different. We implemented from this set of such national standards the Romanian, the Italian, and the Spanish. In order to be able to integrate the new features, the new calculation method, and the new mass and mass combination concept, we had to rework several panels of the software. Therefore, we reworked the panel which defines the seismic effect. We created also new panels for the masses and mass combinations. Masses and mass cases and mass combination, as I said already before, hasn't existed in ConSteel before. Now we have two options to define masses, which will be directly used for the dynamic calculation. Masses can be created during a conversion, automatic conversion of any of the existing load cases, and also additionally the user can select a point and place mass directly on the structure at any required location. When we convert load cases, it's important to note that only the vertical load component will be considered and converted into a mass. By default, each mass which is placed on the structure has degree of freedom set to 3 in each 3 directions of the seismic, of the possible directions. The masses which will be considered for the dynamic analysis will be always grouped into combination. A combination may contain any number of converted load case into mass case or user-defined mass with the appropriate combination or other factors. And this way the designer sets the mass to be considered during the dynamic analysis. In order to be able to handle these new mass cases and mass combinations, we created additional tables which are very similar to the well-known tables of load cases and load combinations. As I said, one of the most important part of today's presentation will be to show what are the new calculation methods which are included in ConSteel 11 to overcome the problem of this CQC combination problem. As I said before, ConSteel needs loads in order to perform those stability verifications, which are the key and the main feature, one of the main features of ConSteel. And as I said also, the CQC method, which is the reference method of Eurocode, doesn't give such loads, therefore the results cannot be used for this purpose. I will speak very much in detail about all the methods, but just briefly we list that there are 3 methods included in ConSteel 11. One is called in the software a single dominant mode. In this mode, which is very similar to the well-known lateral force method of analysis, here in each direction of the seismic excitation, one appropriately selected vibration mode is selected with the appropriate amount of mass, and this without hesitation, without any problem, creates loads, and then these loads can be used without any problem for the other steps of design. Of course, there are cases when Eurocode doesn't allow this simplified method to be used. Plus, there are also cases when using of this method will create a safe but not necessarily economic solution, and therefore might not be the interest of the engineer to use this method as it is. But it gives a very good first view into the behavior of the structure. We have the second method, calculation method, which is implemented, is called in the software as all modes CQC summation. It means that we consider all the modes which were calculated, and we will use the well-known CQC summation method. This method is fully equivalent to the Eurocode method of modal response spectrum analysis. So we select a spectrum, and then all the necessary buckling modes are calculated. The user must check if the total mass participation reaches the minimum 90% of the mass, and if this has been reached, certain results are excluded which don't produce high enough participation of mass, and then the rest is calculated using the CQC summation method. We can see on the screen the result of each bending moment, displacement, diagrams, but it must be also remembered that for such results we can only do cross-section verifications. For such results, if the user selects this approach to define the seismic effect, then it will not be possible to perform stability calculation. And then the third option, and this is probably the most interesting, it is a method which we call the selected modes linear summation. There is no such included in Eurocode 8. This is a method which is a bit similar to the situation if somebody wants to use a buckling shape as imperfection, but then it realizes that there is not one single buckling shape, but prefers to use also other buckling shapes together with this buckling shape. So for example, wants to use the fourth or the fifth or the 10th buckling shape with a different amplitude, and then says that this is now the total set of imperfection which will be used for a second order analysis. Similarly to this, we have also made it possible for the user to, differently from the single dominant mode where always just one mode is considered, here the user will have the chance, based on his knowledge of the structural response, which is well shown, the user will have the choice to include the effect of higher vibration modes together with the dominant one, set appropriate coefficients, and approximate forces which belong to these vibration modes to a result which is very close to the results obtained by the CQC method, with the huge difference that these are still loads, and then these loads can be used for all the additional calculation in ConSteel 11. So this is a method which allows the engineer to adjust loads to the required level and then continue as usual with stability and sensitivity calculations. There is here a table. I'm not sure if it is well visible or not. These are all 4 different types of seismic calculation. On the very right column, you see the column of the manual seismic loads, which means that the user has calculated the loads by other way, not through the use of the calculation features of ConSteel, defines nodes at required loads at required nodes, sets this load case as a seismic load case, and then performs the calculations without any special dynamic calculation. And then there are the 3 previously mentioned calculation methods, which are all based on dynamic analysis with the response spectra. You can see in this table a summary of what type of verification can be done and which type of other verification cannot be done in function of the way how the seismic effect was defined. For example, quite logically, for those methods where the result is a force, then we can do second order analysis, buckling analysis, and sensitivity analysis. for those type of methods which do not result forces, only final maximum values of internal forces. For such results, we can do only global check, cross-section checks. It's also important to note that, of course, masses we don't have in case we defined the manual loads, but we need masses for each other cases where dynamic calculation will be performed. The consideration of masses and the full procedure is fully automatic if somebody selects the all modes CQC method, so the software knows exactly how to combine the results of each vibration mode. The only job of the engineer in this case is to make sure that enough number of vibration modes were calculated in order to reach the minimum limit of 90%. But if enough vibration modes are calculated, then everything is done automatically by the software. Also, the single dominant mode is also fully automatic. Here you don't even have the problem to calculate many buckling modes. In a good case, it's enough to calculate only 3 buckling vibration modes, and the software will find the appropriate vibration mode for each direction and set the masses automatically. So these are automatic methods, and the selected method with the linear combination, this is a tool for the engineer to fine-tune the results. This is not automatic. So in this case, the user will have to set the appropriate factors of each participating vibration mode manually according to the results obtained by CQC, probably CQC method, which is considered as the reference. I will start now with examples. The first example is a console which has a fixed base and has 3 points where point loads. In this time point load. Later I will show the same with masses. So as you can see, I applied a quite big force at these points. Now when I go to the load cases, you can see that we also reorganized a bit the sequence of the load group and load case. Now it's exactly the reverse as it was before. And now I don't need to indirectly set that I want this load case called loads to be converted into mass. This option doesn't appear here because everything will be clearly set by the user how to convert load cases into masses. So this is not just automatically first set here in the picture, first screen, and then not seen anymore. There are special screens for the mass case and mass combination creation where this all method can be controlled. So now I have only just one load case. I don't have self-weight considered. I have these 3 loads, and when I would like to create my mass combination, then I can select. These are already new dialogues on the software. If I click this very first button in the mass tab page, then I can, on the left side, I see a list of all the existing load cases which are existing in the structure, and I can select by placing an arrow into the box before the name of the load case. I can select which are those load cases for which I want the software to create an equivalent mass case. The mass case will have exactly the same name as the load case, and it will contain the result, the equivalent result of the load case. As I said at the beginning, only vertical components are considered. These are converted by dividing by the kilonewton values divided by the gravity acceleration, and then we convert these values into kilograms, and these kilograms will be included in the mass case. Additionally, the user can define any number of manually defined free mass cases. Of course, if a mass case is defined, there is no automatic conversion of an equivalent load case. So in that case, the mass is just a mass without any load type of representation in any of the load cases. Okay, so when I select the loads and I push apply, then the load case is created, and then with the load combination with a symbol similar to load combination, but this is mass combination, I can define what is the mass combination which I want to use for dynamic calculation. There is always a default mass combination called mass combination 1, which is always there. And here I can say what sort of composition I want using the converted load cases into mass cases and the manually defined mass cases. In this case, now I have one time the load case. This is not automatic. There is no wizard to make this definition, but usually this is a very easy, just one line definition for the mass combination to be considered for the building. Once I define my mass combination, I can use it for the dynamic calculation. Let's go back again now to the load cases, and now let's see the seismic load case, which has been added to the design, to the project, because I want to make a seismic verification. Immediately there is a choice to select if this seismic effect, this seismic load group will contain a seismic effect calculated based on a response spectrum with dynamic analysis, or this will be a manual seismic load. If it's a manual seismic load, then I need, as a user, place the required amount of forces at the appropriate nodes, which are modeled the effect of the seismic excitation. There is nothing calculated by ConSteel. These loads are just accepted as they are given by the user, and then, but the combinations which are generated by the software the seismic combination will contain the forces as specified for this load case. If I select spectrum-based, response spectrum-based type, then I need to define a response spectrum like it was before. And now, as I said, also this screen has also changed. In this screen, we can assign the mass combination we just created on the previous screen. So we say that for the dynamic analysis which will be used to calculate the forces, we will use mass combination 1. Here I have the choice to decide which out of the 3 existing dynamic analysis based approaches will be followed: all mode CQC, selected modes linear summation, or the single dominant mode. In this case, I selected the all mode CQC, which is the difference. Then we can also define the response spectrum to be used for calculation. The response spectrum is, as I said, we support Eurocode 8 or similar national standards, so the definition of the response spectra follows the logic of Eurocode 8 to define a response spectra. The response spectra, basically as we define by Eurocode, will be an elastic response spectrum, and then later on, if the user defines the appropriate Q values, then we can create an equivalent design spectrum which uses the same parameters like defined for the elastic spectrum, but of course the accelerations for each vibration second will be different. Based on, we can say if the spectrum is horizontal or vertical, and we can also nicely see at each point along the horizontal axis, and we will see what is the appropriate acceleration which is given. So we can see the horizontal and also the vertical spectrum. We have set always the accelerations, we haven't set Q values. This is an elastic spectrum. Regarding displacements, we have 2 options. Unfortunately, I just realized that I haven't started the developer version of ConSteel. This is the release version. We will very soon release a new version where this will look a bit different. No, sorry, it's okay. So regarding displacement calculation, there are 2 options in Eurocode. One option is a simplified option, is when the user doesn't create any additional spectrum, will continue to use the design spectrum, but in order to have the right accelerations, there are additional QD factors additional QD factors, which basically will increase the acceleration back to the level of the elastic spectrum. These, of course, these QD values should be always in strong relation with the Q values which are defined by the engineer. Usually the values are the same, but not necessarily always the same. So one option is, which is a simplified option approved and proposed by Eurocode is, and this is the default in ConSteel, that the ULS design spectrum will be used and the appropriate QD factors will be used, and then based on this converted design factor we calculate the accelerations and we calculate the displacements. There is also another option if I want to specify directly an SLS elastic spectrum for the SLS calculation. Here again there are two options. One option is to change nothing except the same spectrum which has already been defined. You remember that actually we defined an elastic spectrum there. It will become a design spectrum once we define the Q values. So now if I don't specify any other spectrum, I just accept the same spectrum, it will mean that the ULS, for the ULS combinations, the software will use a spectrum which is a design spectrum based on these values as defined, and for the SLS we'll use an elastic spectrum which is based again by the same values. We can also see at the bottom, in that case there is no big visible differences because the Q and Q1 values have been chosen as the same, but you can still see that there is a small difference at the zero acceleration, zero period part of the diagrams, that there is a known difference between elastic and design spectrum. In some cases it might be important to define another spectrum for the SLS combination, like for example the case of Italian code, where there are different accelerations and even different soil parameter defined for the spectrum which is to be used for serviceability verification. In that case, by the usual way, the user can define any other type of spectrum, again elastic spectrum, and then for the SS verification this other spectrum will be used. Okay, so now in this case I just accepted the same verification and I will use the ULS spectrum. And one more thing, of course I need to create load combination. Load combinations haven't changed drastically. The wizard still exists to create those combinations, load combination which include the seismic effect, but you can see on the right side of the column that there are some additional columns to handle seismic effect. There is direction 1 and direction 2. These are the two principal axes of the structure, horizontal directions. As I chose not to consider vertical seismic, therefore the third column is missing now. So I speak about the acceleration in the two orthogonal horizontal direction. And you see that which is the combination of the directions which are considered to act at the same time. In this case, for example, the acceleration direction 1 was taken with 100% value, and simultaneously the acceleration from the perpendicular direction with 30% value. Plus you see also the alpha values which are now set as auto. Alpha is the factor which shows the sensitivity of the structure for second order effects. If you know Eurocode, then you can find a calculation method which shows how must be verified if for a given structure with its stiffness distribution and mass distribution and the calculated generated seismic loads, what is the ratio of the base shear force at each level compared to the masses, vertical loads, and the height of the story. And from this one can calculate a factor which shows how sensitive the structure is for the second order effects. Eurocode 8 mainly assumes that the user will do a first order calculation for seismic action. That's why it's limited. What is the applicability range of a first order calculation? If the structure starts to be sensitive for second order effect, then within certain ranges a value for this alpha can be calculated with the formula given in Eurocode. ConSteel is able to calculate these values. or if the structure is very weak and would expect it to show big second order effects, then the structure is not adequate, must be strengthened, and the calculation results cannot be accepted. Auto means we accept the value calculated by ConSteel. Changing it to any other number, even to 1, will use that value which was specified by the user. Okay, so once we defined the load combination, also just the last page, which is the analyze, which has also substantially changed and reorganized, we can see that in each line there is a new additional arrow, and by pushing the arrow, another window scrolls into the screen where the other settings can be defined. Here now I have for this calculation 2 combinations. One is the seismic action, other was just the normal ULS case, and now these are by default first order calculation, nothing interesting. And then here below is dynamic analysis, because I selected a seismic calculation method which requires a dynamic analysis, and this has automatically be switched on because the dynamic analysis is compulsory with the mass combination 1. So the first line, you can see that it's already switched on, a dynamic calculation using verification spectrum with the mass combination 1. This is a response spectrum type of analysis. There is also by default also a second line which is not set automatically. This is the line if somebody wants to define another type of dynamic calculation which is most probably not a seismic type of dynamic calculation. So I mean vibration of a floor beam or a rafter or any type of dynamic calculation. Usually these are not response spectrum based, so therefore the column for response spectrum is not switched on, and of course in such case no spectrum can be defined, only a mass combination. It can be the same or any other type of mass combination. Okay, so now once everything was done, I can start the calculation, and then for the results, the well-known first order results, there is also another sub page or sub, I don't know what tab, which is called Seismic MRSA. MRSA is Modal Response Spectrum Analysis, and ULS means that based on the ULS spectrum. And then here I can see the mass combination which was used for the dynamic part of the analysis, and I can see the calculated vibration modes, the values in hertz and seconds. I can come to dynamic shape and see the well-known shape, and also I can do an animation like if it was before. But not just seeing the vibration modes one by one, but very important that I can see what are the forces which appeared in this vibration mode at certain nodes of the structure, and not just see the loads, but I can see also the deformation which is a result of these forces, and I can see also all the necessary internal force diagrams, and I can see also reactions. I can not only see it in the X, but also in the epsilon direction. Okay, so in both directions, I can see the results. In this case, because we had a 2D structure, we have nothing in the vibrations in the other direction, because I placed supports in order to make sure that the structure will not present vibration modes out of plane. In case the user selected the CQC method, because the summary of the CQC based buckling modes is this quadratic method. It's not easy to do by hand. We show also additionally what is the end of the calculation. As I said, in case of CQC, these are not forces, only diagrams of internal forces. That's why we cannot show forces. There are no forces, but we can still show the deformations, and we can also show internal forces. It's important to note, maybe you have already realized, that sometimes we call the direction as 1, 2, and Z, and sometimes we call the direction as X, Y, and Z. X, Y, and Z are all the sub-results of the calculation. The software for each calculations considers the model as it is built. Its stiffness matrices and mass matrices are all built based on the global X, Y, Z coordinate systems as defined in the ConSteel model. So all the sub-results are understood in this system of coordinates, but the summed result, which is the end of the calculation, is already converted into the direction of the seismic excitation. In very rare case, it may happen that the building is not falling into the orthogonal XY coordinate system, but somewhat is rotated. So in that case, the 1 and 2 axes is not fully are not exactly the same as XY, but in normal case, 1 is equal to X and 2 is equal to Y. Okay. And now if I would like to see what is the result of my calculation, then I can go to the so-called SEI, which I defined as the seismic combination, which includes not only the horizontal loads from seismic action, but also consider the vertical loads from those 750 kilonewton of forces which have created this seismic effect. Because this was a calculation with CQC methods, I cannot do stability calculation. I cannot even select sensitivity on this page because this sort of method doesn't allow such calculations to be done. Just quickly review again what has happened. So we calculated the 3 first vibration mode. The software, as also in previous version, is able to show the mass participation. I just show again quickly that after the analysis has been performed, there is a so-called analysis report, which has also existed in previous version 10, but we extended it with additional information. So spectral acceleration top page shows some information about which combination we use. We can see which verification, which spectrum is used or shown, and we can see that for each calculated vibration mode, which is the position on this diagram where the vibration mode in seconds is shown in the horizontal line, and the appropriate acceleration is shown in the vertical line. We also show here with SD this acceleration value. So just by scrolling through the different vibration modes, the user can nicely see graphically how the structure is falling into the different parts of the spectrum. If we go to mass participation, this is a well-known top page, which has always existed before. We can see that now if we concentrate on the first 3 lines, the sum of the first 3 numbers exactly 100%. The first vibration mode has a mass participation factor of 0.71, second has 0.23, and the third has 0.06. So now if I come back to my presentation, then you can see these 3 values here, and these are the forces which were calculated by ConSteel based on the mass participation of the given vibration mode, and these forces are applied at these nodes. As I haven't selected any vertical seismic effect, and only all the vibration modes are in the plane of the paper. Of course, all the forces are only in the plane of the paper. For each of these set of forces, vibration modes, ConSteel is able to calculate the bending moments in all the internal force and displacement diagrams. Now let's speak about bending moments, because usually this is the most interesting in case of a design of a console. So you can see now the bending moment diagrams of each 3 vibration modes, and you can see the values which are calculated at the base level, the first level, and then the second level on the structure. Something a bit strange is visible. This is a result of an artificially strange configuration. The structure is actually not even able to carry the loads. It was just made to show something a bit special. Usually, there is always a dominant mode in case of a simple structure, which produces the biggest values of displacements and internal forces, and then there are additional vibration modes which in certain parts of the structure may produce something important, but generally it's not of global importance. This is always just of local. As you can see, the first vibration mode is dominant at the base, 2300 compared to 722 and 127. It's also dominant on the first level, but it's not dominant on the second level. The second mode produces a much bigger bending moment value. This is simply just because the first mode has a very big vibration, period of vibration, therefore the acceleration was only 2.8 meter per second on the quadrat, but for the second vibration the structure is much stiff, and for that a 9 meter per second, so an almost 4 times bigger acceleration belongs, and therefore the bending moment becomes very high at the second level, much bigger than from the first one. And the third is already producing usually much smaller than any of the other two cases. Now if we calculate the CQC result, then we can see the results, and the values are almost always equal the same as the values of the first mode. So for example 2308 at the base, and the final is 2423 at the base, so it's almost the same, with the only difference that at the second level, where the second mode was dominant, not the value which belongs to the first, which was 340, but a value which is much closer to the value of the second mode, which was 546. The result of the CQC summation results produces from this 340 kilonewton-meter of the first mode and the 546 kilonewton-meter of the second mode gives a total sum of 654 kilonewton-meter. It is just a small presentation here for those who have not too much experience with the CQC summation. This mode basically will always result the biggest of the values to be combined. So if you combine several values and there is one dominant and the rest are smaller, then the result will be always very close to this one dominant load. As you can see on this picture, now I have two sets of values. One is red, the other is blue. Where the blue is small, there the red is big, and just the reverse, and the green is the CQC summarized value of it. And you can see that basically it will always give the answer of the biggest, with the exception of the case where the two values are going to be similar to each other. In that case, the CQC result will be bigger than any of the two. So it's somehow this method is always favorizing the biggest values. So back to the console case, at every location we got a result which was very similar to the first vibration mode, but on the second level it was very similar to the result of the second vibration mode. This typically also shows that if for this structure somebody would make a design based simply on the first mode, then probably would have problems with under design at the level of the second level, because that part is dominated by not by the first but by the second vibration mode. As I said, if we try to make a single dominant mode calculation, so instead of making the calculation verification effect and not the all mode CQC, but we would select the single dominant mode, the software would find the dominant mode, which is obviously dominant means which produces the biggest base shear force. This is obviously the first, so it would select the first mode and we calculate the forces based on the first mode only. Now there are here two options which we could do. The result of the dynamic analysis has resulted that to the first mode 71% of mass belongs to. So in the first table we calculated the forces which would correspond to this 71% of mass. And as you can see that when we compare to the CQC result of 100% of mass, then we can see that values close to the base are very close to 1, 0.95. This is still a bit less than 1, so it means it's theoretically unsafe, but as I said at the beginning, at the top of the building where we are at the second level, where the second mode dominates over the first, we see that the value which we would calculate with the 71% result of the first mode only, we would seriously under-design the structure because the intent bending moment in that case gives only 62% of the reference value obtained by CQC. Because of this, to provide an additional safety for most of the cases, when the user selects a single dominant mode, ConSteel will disregard the mass participation of the selected vibration mode and will always apply 100% of the mass. So in that case, the second table below shows already the results which belong to not 71% but 100% of mass. So first vibration mode as it is, and the loads and the masses are increased artificially to 100%, and that's why forces are bigger. Now you can see that at the base of the structure we are actually much above the 1, but at this critical part of the building we are still below 1. So it means that even with this increase of additional safety, for such a structure, which I said at the beginning, it's an artificially created structure to show a dominance of the second mode. For this case, the single dominant mode doesn't give appropriate answer. Here comes the third method, where the user will realize that it's about a structure where a safe design for certain parts of the building cannot be done based on the dominant mode, because there are parts of the building where higher vibration modes have significant role. And here comes handy this third option, which can be again set on the verification effect and select selected modes linear summation. Once the user has, and I will load this file because it's much quicker to play with that, on the console. Selected modes. If the user selects this type of calculation method, then first of all it's important that the run must be done at the beginning, where we get the results for each vibration mode, the modal shapes and the mass participations. So it is important to first run the calculation, and when the calculation has run, there is even a note here that first a vibration analysis must be performed, and once it has been performed, there is an additional table where the user can select what sort of combination of the vibration modes he wants to consider. So for example, here as visible, I said that now I recognize that I must consider also the second vibration mode, and for example here I said that I would like to use a 1.2 factor on the results on the forces from the first vibration mode, and I would like to add to it the forces of the second vibration mode multiplied by minus 0.4. Minus means that by calculation at that level where I would like to study, the forces from the second vibration mode had a negative sign. That's why I need to convert it back to finally add the two values. I would like to increase the effect of the first vibration mode. So now, if I come back to here, even graphically I can see that the first page you see the forces from the first vibration mode. These forces will be multiplied by 1.2. Then you see the second come the forces from the second vibration mode. These would be multiplied by minus 0.4, and finally it will result this set of loads, so 209, 126, and minus 54.4. And this will be the load case, which will be considered as a result of seismic effect. Now if I calculate the bending moments, again, I will see that at that my critical level, here at the second level, I have a very nice correspondence of my bending moment to the reference value of CQC. So it means that it might happen that it was just a very easy structure, and of course it's not very representative, but it maybe explains well the situation. It might happen that the first mode is not acceptable for certain parts of the building, either because higher vibration modes must be also considered, or it gives too much of safe side result, and therefore the user has the chance to create additional load cases based on the forces of the pre-calculated vibration modes, and with these, with the appropriate factors, can fine-tune the results to give such forces, such internal forces at the studied part of the building, which are close to the CQC reference result. It's important to note that these will be always valid for that part of the structure for which they were fine-tuned. So it's not necessarily the right value for other parts of the building. Now, if I come to my second example, that I will just very quickly go no, still on the first example, I will just show what would be the situation if I define masses instead of loads directly. Unfortunately, again, I will run out of time. I will need about 15 minutes more to finish this presentation, depending on if you can stay longer with me or not. I would say goodbye for those who need to leave, but hopefully most of you can still stay with me and continue till the end of the presentation. So now in the first, the console must, I open now another file which I created before, where I would like to show that what happens if I don't have loads to be converted into masses, but I would like to specify the masses directly. In that case, I have again the same load cases like before, and then if I come to mass, as you see, I haven't selected the load case to be converted, but instead of that, in the mass case, which is the mass case, this is the name of that manually defined mass case into which I want to put the kilos myself. I select this mass case, and then with this function point mass, I can define at any of the points the specified amount of kilogram. This will be considered in each 3 direction of freedom, which will be then later controlled. If we speak about seismic design, then we can say that if we have seismic verification in Z vertical direction or not, but the kilo itself, so the mass will be placed with 3 values in each 3 directions of the space. So once I define the masses, then it's nothing special, the same combination table for the mass combination. Again, in this case, I don't have any converted load case. I have only my mass case, so therefore that's the only column I see. Again, I create mass combination, and then the rest is the same. It's important that in that case we have only masses. So if I wouldn't have these 200, 250, 750, 750 kilonewtons loads, only the masses, then I could give a correct dynamic result. But of course, in order to create my load combination with the seismic effect, these forces would be missing. So of course, I need to create those as loads. To create masses, in many cases, it is very helpful, especially, I will speak also some words about that, if somebody would want to make a sort of mass condensation of the structure. It can happen in case of bigger structures that by placing just loads on weak elements and convert easily those loads into masses, those big proportion of the masses will appear on very weak elements, and when I try to calculate vibration modes, I will see that unfortunately all these weak elements are vibrating, and I'm physically unable to calculate the required number of vibration modes. Therefore, it can help that this is not an automated process, this is by the user, but the user can manually concentrate the masses into the required positions where the structure is strong enough, and this way can help to the software to find the required and appropriate buckling vibration modes. Now, I go now to my second example quickly, which is a 2D frame. It's a 2D industrial frame. It contains some features which I will not speak about. It's because now we concentrate on seismic design only. This is an industrial type of frame, 2D frame. We have corners placed with the corner wizard. We have tapered columns and beams, but this is not of interest at the moment. We have again different type of loads, and we have also a seismic action, which is again a response spectrum based, to which belongs a seismic effect which uses the mass combination, called the mass combination. We will use the all-mode CQC summation, and we will use the spectrum as defined on this page. And I also come to analysis. On the analysis page, again, dynamic analysis is set. I don't want to make free vibration calculation. I would like to make only the response spectrum analysis with spectrum 1. I would like to consider 3 vibration modes. And regarding the combinations, we can see the normal combination. We can see also the seismic combination. Because I selected CQC method, I cannot switch on sensitivity for those combinations which include seismic effect. But first we will start with this because this is the reference. Okay, so we will use a CQC summation. For this combination, we can only do stress verification, cross-section verification. We will not be able to do buckling verification because the result of CQC summations are not forces. Okay, so if I make now the start the analysis. Then again, we see all these different values, sensitivity, buckling, second order, first order, but now I go to seismic MRSA. Again, I can see the mass combination, which was the name of my mass combination. I see those 3 vibration modes as I defined, and I see also the arrows. It looks a bit terrible, but if somebody zooms into it, then you can see much better what are the forces which were calculated by the software to each node. Of course, we can play with the arrows, and for each vibration mode we can see what are the values. As you can see, because the masses had also degree of freedom in the vertical direction, we have also forces in the vertical direction together with the forces which are in horizontal direction. We cannot see only the forces, but we can see also the deformation of the mode, and also we can see the internal forces. As you may say, when I select between the different vibration mode, there is visibly the ConSteel starts to make an analysis. In order to save calculation time, we expect that the user will not always want to see always the results of each calculated vibration mode, like bending moments, displays, and everything. We don't calculate these. We calculate, but we don't save the results of these calculations. And therefore, when the user wants to see them again, we'll have to wait a couple of milliseconds, or in case of bigger structure, of course, a bit more, but it's not a substantial amount of time. But in order to save the size of the files and improve calculation time, this will be always calculated if it's needed. Okay, now so for that, now we can see that the bending moment diagram from the first mode is like this. The bending moment diagram from the second mode is like this. And the bending moment diagram for the third mode is like this. We can see all the values here. And also displacement, we can see also reactions and everything. And additionally, because we speak about the CQC method, we can see also the end result of the seismic calculation. This is the bending moment diagram with the CQC summation. Values are always shown. Contrary to some other softwares, we always show just the value of one sign, either positive or negative. Of course, when we create the load combinations, then we will always have the seismic effect with +1 or with -1 value. So we will get always the plus and also the minus values in the combinations. Okay. Coming back, so we see the end, and then this will be used in the seismic combinations to perform cross-section verifications. For this, we cannot do stability verification. What we can do if we want to do stability verification for this structure, first of all, before going that, we can come here and see what was the mass participation of different vibration modes. We can see that as expected, the first vibration mode dominates everything. The mass participation is 0.88, which is already alone almost equal to the 0.9 lower limit. So theoretically, it's still not okay by Eurocode, but in practice, it's quite okay to accept the results of the first vibration mode as appropriate. So let's see the 2D 2D frame dominant mode. Here the only difference was that seismic action, single dominant mode. So in this case the software selects the single dominant case, which will be the first mode, and when I come to my combinations, 43 is a combination which already contains the second order effect. Here I will see a bending moment diagram which already, it's probably, yeah, it's maybe not. Here you can see that this is already a bending moment diagram which contains the results of the vibration mode considered with 100% of mass. So not only 88% of the mass is considered, which would be automatically the result of the dynamic calculation. But to be on the safe side, we take 100% of the mass, and therefore the internal forces are a bit higher than it is required. We can see as reference what will be the internal forces with the CQC in the combination. So you see it would be 239. This is the precise value. In this case, we have a bit higher, 261. So it's about 15% higher, but it's safe side. And we can do, and this is because this is already a force, we can do stability calculation and everything for this. So for example, for 31, we can see buckling for the 31. We can see that this is the buckling shape for this combination 31, which includes a dominant mode result of the seismic action. If somebody feels that this over design is not acceptable, then again may use this magic of the selected modes, and you can come to the file of the selected modes. Typically, if we have a normally configured structure, so not like my case with the ConSteel where I artificially made it very sensitive, normally as a good approach is always to select with factor of 1 the dominant case and add additionally with 0, 2, 0, 3, 0, 5, 0, 6 components, coefficients, all the additional vibration modes in the right sequence. So for example here in this case we can see that I defined a combination of first mode one time and 30% of the third. If you remember, the second mode was creating only vertical displacement. It created 0 base shift force, so that's definitely not interesting. So I created a load combination which was 100% of the first and 30% of the third. So this is a special improved dominant mode calculation with my knowledge as an engineer. And now when I make the calculation, then again, and if I now look to again, they look a bit different, the numbering. But now you can see that this way I created a bending moment of 244, which was basically almost the same as the CQC result. So CQC result was 239, now I have 244. This is an improvement compared to the dominant mode results, which would be 261, so it is much more approaching the correct result. And again, because this is based on forces, this is appropriate to do all the stability calculation. Okay, and now I come to the very last set of results of my presentation, and therefore also to the end of this webinar. The third building is a 3D structure which consists of 2D frames in each perpendicular direction. As reference, we will use the CQC results. On the screen now you can see the values of the CQC calculation. I close this different. So this is a structure as it is, and again I have a mass combination In this mass combination, I took with one value one time the mezzanine load case converted automatically into a mass case, one time the self-weight load case converted into a mass case with one factor, the roof dead load the same way, external was same way, and I said that the life load would be considered with a coefficient of 0.5, and I don't have in this case any manually defined mass case. And when I make the calculation, and again I select the calculation mode as response spectrum based, and I said that this is an all mode CQC method. Now I just quickly show how difference is. Now I defined the Q value of equal to 6.5, and now of course if I choose this one, then you would be able to see the big difference of the design spectrum created with the same parameters and the response spectrum created with the same parameters. The main visible difference is the factor Q, and there is a small difference only at the zero acceleration part, zero vibration, zero period part of the diagrams. Now this is not too much interesting now. So if I see the results, then this would be the results based on CQC, which I will take as reference. And now let's see the effect of different calculation method. We will just check the Y direction of the structure. So this is the Y direction, this is the frame on axis C, which we will study. And now we will see the results of the dominant mode. Let's first see again the analysis result. We will see what is the mass participation, because that gives a good indication of how good the dominant mode will be. We see that in Y direction the first mode gave a very high 0.81 mass participation. It means that it's very close to 0.9. It means that there is a very good chance that for this building the first vibration mode will give a relatively good answer. It should be by minimum 0.9. If we select the dominant mode, ConSteel will take 100% of the mass, not only 81. Now if you see the results, and again just concentrate on bending moment, MY bending moment diagrams, from a dominant mode with 100% of the first vibration mode, then these are the bending moment diagrams, and on the right side you can see these 1.8 and 1.1. This is the ratio between the, let's say, correct number and this value. If the number is bigger than 1, it means it's safe, but bigger the value, it means it's more conservative. The results are higher than necessary. So now you can see that, as expected, the first vibration mode, especially with considering 100% of the mass instead of just the 81, it gives a very good, safe approximation of the seismic effects. All the values are bigger than 1, and it's the decision of the engineer. If it is acceptable to have such a safety on the seismic design, then there is nothing else to do. It's fully automatic, and all the stability calculations, everything can be done, and seismic verification is covered. If by any reason this 1.18 or 1.22 is not acceptable, then there are several other ways to improve the situation. One of the possibility is, as I said already before, is for those parts of the structure where we expect that higher modes have some sort of importance, then we create a combination of the cases. Typically, the first vibration mode gives interesting results at the bottom part of the structure, and as we go higher and higher, we will see that others. So for example, the first mode created, for example, such values at the higher levels like 200 and 110, and if we scroll down the different vibrations modes, we can see that there are some other cases where there are some values which might be interesting. For example, we can find vibration mode number 5, where we can see that there are some values which are relatively high compared to the 100 of the first vibration mode. So the CQC summation of 100 and almost 60 will definitely create a value which is more than 100. So if I combine this vibration mode with the first one, then I can have a much better approximation to to the CQC value. Of course, in this case, I will not take any more 100% mass to the first mode. I will accept the result of 81% for the first mode, and I will manually add masses into the right vibration mode as an engineer, I feel it. So for example, in that case, I created a load case where I took the first vibration mode with a factor of 100% times the 0.81 mass combination, and I took 30% of the combination vibration mode number 5. And as you can see, now very nicely at the 3 upper levels where I wanted to make this fine-tuning, I managed to approach this value close to 1. 1 means that the value is exactly the same as the CQC reference value. You can also see that as this fine-tuning was done for the upper part of the building, this set of vibration modes doesn't give a safe results to those parts of the building where another combination of modes would be relevant. So the dominant mode calculation gave a safe result, but the values were always higher than 1. It means it was a bit of over-design. This is mainly due to the fact that we take 100% of the mass instead of the 0.81. Eurocode 8, in case of symmetric buildings of number of floors more than 2, and if certain other conditions exist, which it's important to remember that this possibility is not always given, but for example, in the case of this building, this option would be available, that if somebody uses a lateral force method, then the mass of the total mass to be considered can be reduced with a factor called lambda, which has a value of 0.85. So it means that if the engineer would create a combination where only the first mode is considered with a combination factor of 0.85, and considering only this very first vibration mode, he could get a result which is, according to Eurocode, which would be very, very close, almost equal to the CQC result. As you can see, especially on the level of the critical part, as we saw that the fifth vibration mode has an important role, this method, which is fully Eurocode compatible, it would be a slightly under-designed for that critical level, but for the rest of the structure, it gives a value very nice to 1. But as I would like to repeat again, this approach to reduce the mass by 15% is only available in certain cases, not always. Our solution to manually combine the results, the forces of the calculated buckling modes is always applicable. We say that the user must always use as reference the CQC results, the internal forces obtained by CQC results, and can always create at those parts where it is necessary the appropriate combination of the vibration modes in order to extend the validity of the dominant mass based simplified calculation. Maybe it's a bit complex now. I would like to make now have a table with a sort of conclusion with the recommended procedures. If during the design of a building a seismic effect is not controlling effect on the structure, but the engineer still wants to consider somehow the seismic effect, then he can decide to use a CQC method. The CQC method will very precisely calculate all the maximum values at each cross-section. For example, if somebody wants to make an SLS verification, then the result is perfectly fine. He can still do stress verification, but cannot make stability verification, but it's not a problem in this case because anyway we know the seismic effect is not controlling the design at all. If this is not the case and seismic effect cannot be disregarded, but we believe, or the engineer believes, that it's still not the most dominant effect on the structure, then our recommendation is to start the design with the dominant mode calculation, looking to the mass participation, have a judgment on how good these single modes in each direction can be. If the value is close to high enough, above 0.7, 0.8, if we have such a structure, then we can be quite sure that the dominant will be quite good, at least as a starting point, and then later during the design, at several critical steps of the design as the project evaluates, it is recommended to stop for a while and make just a spot check to see how the stress levels are compared with the very precise CQC results. So stop for a moment, make a copy of the model, make a calculation of the seismic effects with the CQC method and compare the stresses. If the stresses are comparable with the stresses obtained from the dominant mode, it means that we are on the good way. There is no need we can continue the design with the dominant mode calculation. If at certain parts of the building it is visible that there is a bigger than acceptable difference in positive or negative direction, then locally for those parts of the building the designer can create additional manual vibration mode combinations where he can fine-tune the result as close as possible to the reference CQC value. If the seismic action is very much controlling the design, then probably doesn't make too much sense to base the design on the dominant mode because it will be quite misleading. In such a case, it is recommended to start immediately with combined load vibration modes. It's important to remember that this is not automatic. So the combination of the cases must be done manually, and it's also very important to remember that as you develop your structure and masses are placed on the structure or stiffnesses are modified, it can easily happen that the sequence of different vibration modes will change. So the definition like 1 time the first and 0.2 times the 20th may not be valid after the structure has changed, and maybe the appropriate vibration mode is not the 20th anymore but the 19th or the 21st. Okay, so it's important to note that ConSteel will always accept those definitions as they are without analyzing if the values might be correct there or not. If the seismic effect is just controlling SLS, so there is no load bearing problem, then again the CQC method gives perfectly fine result, and in such case there is no need for dynamic calculation. So that was the end of my side. Sorry for a bit longer than expected or forecasted before, and I'm sure that it was also not too easy to understand. So I would like to say thank you to all of you, and I will conclude now this webinar and see you next time. Bye bye.